Hi everyone and welcome to this new video in which I continue my Linux Privilege Escalation series. In this video we will talk about using kernel exploits. So we will introduce the idea of kernel exploitation. Now in the previous idea we discussed a similar thing which is binary exploitation. So binary exploitation. And the idea of binary exploitation was that we had an elf binary, so an executable that can be run on Linux system, and this elf binary had a memory corruption issue, a buffer overflow. Specifically, we had a stacked base buffer overflow. Now, by using this buffer overflow, we were able to hijack the normal execution of the program and obtain a shell. So we were able to take the program as it was written by the developers and use it to execute our own code. And this is an example of binary exploitation. And then we discussed, if the program was owned by root and maybe had the setuid bit, then we would be able to obtain a shell as root, and therefore we would perform a privilege escalation. So the idea was that one way to do privilege escalation is you consider the elf binaries in your system, you analyze those that are vulnerable, for example, to memory corruption, and you try to exploit them through binary exploitation techniques. Of course, the exploit we developed was very simple, because the point was not to introduce the modern techniques of binary exploitation, but rather to give an idea as to how this is done, how it works in principle. And then at the end of the video, I mentioned the difference between user space programs and kernel space. So what's the difference? I mean, what is a kernel and what is kernel exploitation? So we can start with this question. As always, I hope the video is enjoyable. If you find it so, please leave some feedback, subscribe to the channel and share this video with like-minded people to help me grow. Thank you very much and enjoy the video. So, what is a kernel? Now, the kernel is one of the lowest software layers found within a modern operating system. So we're talking about software, but at the same time, we're talking about one of the lowest software layers in the abstraction stack that is built in modern computers. Now, what is the kernel used for? When we talk about software, usually software is written to abstract over something else. In particular, the kernel is used to abstract away from the firmware and the hardware layers, which are complex and difficult to interact with. So what is the idea here? Let's say that we are a developer of a video game and we want to write code for a video game. Now, instead of having to know the specific details of the machine that we will be run on, which we would need without kernel. So if we had no kernel, all programs that we write, we will have to know all the details of the firmware and the hardware of every machine they will run on. And this, of course, is really difficult because you're just a developer, you just want to make a game, you don't really care that much about the hardware details of the computer of the people who will buy your games. So over time, over the years in the history of computer science, people came up with this idea of a kernel. The objective of the kernel is to interact with user space programs, is to give user space programs an abstraction over the hardware and the firmware. So the kernel therefore acts as an abstraction layer on top of which modern software runs. So that when I, game developer, write a new game, I will just use the APIs offered by the kernel and I will stop there. I will not go below that layer, I will not go below that level, which means that all the firmware, all the drivers and all the hardware, I will not care about that too much. Maybe I can put some hardware requirements, but I will not care about the specific hardware details of the machine I'm working on. It's just gonna run. Why? Because when the user space asks, for example, write in this memory address, write a pixel on the screen, the kernel is able to translate this abstract request into the operational procedure needed for interacting with that specific monitor, with that specific memory RAM, and so on and so forth. And this picture essentially represents what we just said. User space programs do not talk to the hardware or to the firmware, rather they talk to the kernel. And it is the objective of the kernel to translate the request with the appropriate language and so on and so on and so forth. So for example, let's say that we have this very simple program. So here I've written into the simple.c file. It's a really simple program, as I said. It just prints a string essentially. And we can compile this with gcc simple.c -o simple and then n to execute it. Very, very simple. We just print a string. Now, anytime we have a simple C program that prints a string as the one shown below, like this, with printf hello world, internally, this program will make use of system calls, which are APIs implemented and offered by the kernel to interact with the underlying machine. So the abstraction layer that is between the kernel and the user space program, such as this one, the one we just executed is a user space program, and it prints a string hello world. This API is made up of system calls. So the single functions are called system calls, which means that different kernel will provide different system calls. And for example, even the Linux kernel, depending on the version, will support different system calls. As it grows, it can support more system calls, it can deprecate some of the old ones, and so on and so forth. It can even change the arguments to some of them sometimes. Now there is a really useful program we can use to list out all the system calls that are made during the execution of a given program. And this command is the strace command. So for example, here I just executed simple and we got the string, right? This seemed like a simple operation. Well, in actuality, there is a lot going on that we do not see. If you want to see, for example, all the system call that the user space programs makes to the kernel, we can use strace and then we do simple. And notice what we get here. We get a bunch of lines here. Now, each line is representing a different system call. And the way that the strace prints them out is for debugging purpose. In particular, for example, the first system call we make is the exec va system call. This is used to start a new program. Essentially, what the shell does is first it forks its own process, and then in the new forked version, it's gonna do an exec va. So it's gonna clone itself, and then in the new copy, it's not gonna execute the same old shell, but it's gonna execute the new program. And here we see the arguments that are used for the system call. So we see, for example, this is a memory address, because sometimes in C you have pointers. So here we put strace prints out the memory address that at time of execution was the value of the pointer variable. So we have this exec va, and then here on the right we have the return value of the system call. Then for example we have brk, we have access, openat, fstat, mmap, which is used to map memory areas, close, openat, read, pread64, fstat, once again mmap, a bunch of mmmaps. It's like arc, prctl, set id address, set robust list. This is all to say that there's a lot of interaction that the C program makes with the underlying kernel. And finally, there is the write system call, which is the one actually used to write to the screen. And here we put this one here as first argument, which represents where we want to write the string. In this case, 1 stands for standard output. It is the file descriptor, the ID, that represents the standard output, which in this case is simply the shell. We are simply printing a hello world. So this is all just to say that even the simple act of printing a string actually requires a lot of interaction with the underlying kernel. Now, why do we care about that? This is the interesting part. So why are kernel exploits especially dangerous? Now, since the kernel has to interact with the underlying hardware and firmware, it requires a lot more privileges. This is natural. It requires to be able to configure the processor in a certain way, like to configure the entire machine in a certain way. The kernel is essentially the orchestrator behind all the interaction that the computer makes. Therefore, it has to have root privileges, administrator privileges. But remember that the kernel is written in software. Software is a software, and all software can potentially be vulnerable. I mean, even hardware can be vulnerable. However, to exploit hardware, you need a different set of assumptions. To exploit software instead is much more feasible. This means that even code that runs in kernel mode can be vulnerable, and code that runs in kernel mode is run with a higher privileges. So a kernel exploit is a malicious code that uses a vulnerability found within the kernel code, so found within code that is executed in kernel mode, in order to once again hijack the normal flow of execution and execute arbitrary malicious code. This time, however, what is attacked is the kernel of the machine, meaning that the attacker is able to change the underlying configuration of the operating system. It is very different from attacking a user space program, because you are literally inside the kernel, and therefore, for example, you can hide certain stuff, you can disable certain protection mechanism, and so on and so forth. Given you have a more underlying access to the system, you have also more power. It also means that doing kernel exploitation is much harder. To make it simple, in practice, this means that a successful kernel exploitation can result in obtaining a root shell. Of course, this is like very simplified version. In general, kernel exploits are extremely dangerous, also because of rootkits, for example. So the idea is that a rootkit is a malicious piece of software that is installed in your system and that is used to like monitor your activity within the system, to exfiltrate data from your system to some attacker machine, to wait maybe for a specific time in order to attack, to inject payload, and so on and so forth. And rootkits can be installed once you have root privileges and once you're able to inject malicious code in the kernel. Now, of course, there are many different kernel exploits that historically have been found, so there are known vulnerabilities in old version of the kernel. New ones are being researched right now, and they will be published like in the future, and so on and so forth. So one of the things that is important to do is to enumerate the kernel version. This is actually pretty simple. You can use the command uname-a. So you can just use this command, and among here you find this Linux, here the host name, and here is the kernel version, like 5.15.0. So this is the kernel version. You can also use, for example, in my case, uname-r, and it just gives me the specific kernel version, 6.9.7. So to showcase a practical example of kernel exploitation, I brought a little example taken from one of the machines in ActedBox. Here we're talking about the Valentine machine. I did not make a full playthrough on this machine. It is a bit old. Maybe in the future I can do. If you're also interested in that, write it in the comment and let me know. So the idea is that this machine, for the final part of privilege escalation, can be approached in different ways. There is an intended way, and there's also a way with kernel exploitation. So we can just go and actually do the machine. Here, essentially, I am within the machine here in Valentine. So I can say hostname Valentine. I will not show how to get here. I will just show how kernel exploitation works with a practical example. To get there, essentially, first you have to find an SSH keys, but that is outside the scope of this video. So at this point here, we are inside the machine, and the first thing we can do, of course, is to enumerate the kernel version, because to do kernel exploitation, you need to have a vulnerable kernel version, and also you need to have a specific kernel configuration. So when it comes to kernel, there are two things. There is the version and there is the configuration. Now, the configuration for a Linux kernel is extremely complex. It has a lot of different flags because the kernel supports a lot of different hardware platforms with different sort of requirements and behavior, sort of. So you can have kernel configured in a certain way for a certain traffic, for a certain processing, for a certain type of data processing, and other kernels for more normal usage, and so on and so forth. So sometimes exploits do not work. This is typically not easy. Of course, it's also important to mention that you must be extremely careful when trying kernel exploits, and in particular, you should not try kernel exploits if you should not make the system crash. It's like if you don't want the system to crash, be extremely careful about trying kernel exploits. This is because if a kernel exploits crash and it doesn't work well, the entire system will crash down and you will have to reboot it and to re-execute it from the start. And this is essentially what happened with the recent CrowdStrike accident. They had a bug in a module of the kernel. It was the Windows kernel for sure, but it doesn't really matter at in this case. Anytime you have a bug in the kernel, you have a kernel panic and the entire system crash down. This is very different from when you have, for example, a bug in a user space program. It's different because a user space program is actually managed by the kernel. If the user space program crashes, the kernel is able to recover the situation, to recover the memory, to recover all the resources that was used for the program, and to assign it to different processes. So there's no real loss. If a single program crashes, you just lose the data for that single program. If a kernel crashes, if the kernel code crashes, if you have, for example, a crash, an exception, an error in kernel code, the entire system will crash down too. So be extremely mindful and careful when you try kernel exploits. So let's enumerate the version for this particular kernel. So let's name it as A. We got a kernel that is 3.2.0, so much older than the current one, because the current one in my machine is 6.9, this is 3.2, so 3 major version behind. And this machine also runs Ubuntu 12.04, so very old Ubuntu. Now, perfect, we have this kernel version. At this point, we can use an utility in Kali. So here down I have a shell in Kali, where here up I have a shell in Valentine. So we can use a utility in Kali, which is called search exploit. So it's called search exploit. How does it work? Essentially, this is a simple command line interface that searches an online database of exploits. I think that this online database is actually downloaded locally, but essentially you have this search exploit. You can just do search exploit and then Linux kernel and then the version 3.2. And then here you have a bunch of results essentially that says, look, all these exploits are for example, this one is kernel version 2.6 until 5.9, 2.6 until 3.9, 2.6 until 3.9 like DirtyCow. DirtyCow was a famous kernel exploit that is a race condition in the way that copy on write mechanism was implemented by all versions of the kernel and a lot of other exploits. Now, among all of these kernel exploits, we're gonna use actually the DirtyCow exploit. So what is DirtyCow? DirtyCow. I will not show it fully, I will not discuss it fully, we will just use kernel exploits, we will not implement it. Maybe in the future I can implement something like that. Anyways, the idea is that this DirtyCow was a vulnerability, specifically it was a race condition in how the kernel internally handle the copy on write mechanism. So what's the idea of copy on write? If, for example, you have two variables like A, which is like hello, and then B, which is like A, initially these point to the same memory area. Because B is just A unchanged, so there's no need to make a new copy of A and assign it to B. They literally point to the same memory area. It's like if you consider the memory, for example, this is the hello, it's written in memory here, at a certain address like X, A points to X and B points to X as well. When you make a change, so when you say like B equals hello world, so when you change B, at this point, what's going to happen underneath is that the kernel will make a copy for the string hello, and then it will change it. So it will make a new copy in memory. Essentially, they exploited the way this mechanism works, and in particular, they had this race condition where, using this race condition, they would be able to overwrite files in the file system that were only readable by the user. So you had a readable file, for example, the etc passwd file this file can only be read by a user. It cannot be overwritten. Like here, the only one who can write it is the root here. But a general user has only read permission over this particular file. Thanks to this copy and write mechanism and to the race condition that the kernel contained in the handling of this copy and write mechanism, a user will be able to overwrite this file and add arbitrary strings. And this essentially allows you to add a new user with a UID 0, which means to add a new root account. So that's the general idea of the exploit. So here I lost myself. I think this is 2 and then this is 3. And then, okay, here, for example, so yeah, so we're gonna use this DirtyCow exploit. Now, of course, there are many copies of the exploit. We will use this one, essentially. We will use this here. On the right, there is this 40839, which is like a unique identifier for the particular exploit. So the way we can obtain it, essentially, is by doing search exploit, then we do -m, and then we put this ID, 40839. And it says, look, this is the DirtyCow ptrace POC data race condition privilege escalation. Here is a link to the exploit. Here is a link to the local file. Here is the URL where you can find the exploit. So if you just go here and we just go to the URL, we find this Linux kernel exploits. So this exploit uses the Pokemon exploits of the DirtyCow vulnerability as a base and automatically generates a new password line. To use these exploits, modify the user value according to your needs. The default is Firefart. So essentially it's going to create a new account named Firefart. Original exploit DirtyCow ptrace Pokemon bypass is this one. So this one is the original exploit of DirtyCow. Echo Pikachu Pokeball, so this is it. And essentially to run, so we can compile with this and we can run with that. Afterwards, you can either su Firefart or SSH Firefart. Don't forget to restore your password. So this is essentially this is the idea. And this is the main. This is the main. It's gonna make a backup file. It's gonna set up the user info struct. It's gonna enter the password for the new user. It's gonna generate the hash. It's gonna generate the complete password file. And then at this point is the actual exploit. So this is the finish of the exploit. Here we create a copy and write on the etc password. As I said, I will not go into the details on explaining this exploit. For now, we will just use it. But the idea is that these exploits are reconditioned to modify the password file and to generate this new line that the code generates. So that's essentially the idea. So now we got it in our local folder. Look at this, it's 40839.c. Perfect. At this point, the objective is to bring it into the remote machine. So we can do that we get our IP address with the ActBox VPN, which is 10.10.14.19. We open a Python server. So we do Python 3, HTTP server 1337. Remember the port. Then we go into the Valentine machine and we do a simple curl, which is installed. Perfect. We do a simple curl 10.10.14.19 1337. And here we put the name of the file, which is 40839.c. 40839.c, and we print it to the standard output. So at this point, we have downloaded the exploit in the remote machine. Remember that within the exploit, there was written how to compile it. So we can just read it essentially. So it says, look, compile with GCC, pthread, lcrypt. So we do this. So we need some libraries. It says, okay, dirty, because this is called dirty. We don't call it dirty. We call it 40839. And now we have compiled it. So at this point, we have compiled the exploit. It's this 40839. Okay, let's check the value of the etc password. We do cat etc password. Notice that we have normal users, and here we have the root user. So this is the state, and we're gonna save this into a file so that we remember. We're gonna save this into the scratch buffer. Perfect. And then we're gonna run the exploit. So to run the exploit, the idea was that we can either just run it and it will ask for a password, or we can run it directly with a new password. So we can say 40839 and then a new password, which I'm just gonna say password, very simple. So let's run it. It says etc password is successfully backed up. Please enter the password, complete line, mmap. So essentially the exploit worked, and it added this particular line to the etc passwd file. If we just terminate the process and we just cut out the new bash, the new passwd, essentially notice here, it changed the file and now there's written firefart. So now we can do su firefart. It's gonna ask us for a password and we're just gonna put the password that we entered previously here. Password, and we have a root shell. The username is firefart, but the ID essentially is 0, which means that we can go to the root directory and here we have the root flag. And so we have successfully exploited this machine. This time, however, we did not use a binary exploitation, we use kernel exploitation. We use a kernel exploits, that is, we exploited the logic that is implemented within the kernel. Of course, we did not do it manually. We use an exploit written by researcher, by other people, and so on and so forth. But the idea is that what was vulnerable here was the actual kernel code. So this is the way we got in. It's kernel code that allowed us to obtain execution as root. Specifically, it allowed us to obtain a write primitive on any file of the system as root. But if we have that, we can modify the passwd file to obtain, to sort of set up an account with root privileges. This attack also uses an interesting fact on how the etc passwd is handled. So if you notice here, all these rows have in the second column an X. Like for example, hype here is an X, gnat is an X, IRC is an X, backup is an X, www, like all these have an X. However, firefart does not have an X, but has an hashed value. So when a user does not have an X here, it's going to be treated as the hash of the password. So sometimes it's not look the etc shadow, which typically contains the hashes. The hashes can also be put in the passwd. And this, I believe, is done for compatibility with older system. So if you're able to just write in the passwd, you can trick the system into authenticating with any user, and you can also choose your ID here, which is 0. So with 0, it means root. It means we have root execution. So essentially, this is the idea for the exploitation. And this in these notes, just take note of this. So just this is it for the practical example. So this is it for this video. Here are some reference. In particular, there is the walkthrough by 0xDF of the Valentine machine. Maybe in the future I will bring a video walkthrough of it. If you're interested, just let me know. And then some references on DirtyCow exploitation, specifically the two exploits, the one we use and the one that was referred in the one we use, and also a blog post describing the vulnerability, which is written in a pretty clear way, so it's very easy to understand. So the takeaways for this is that exploitation can not only happen in binaries running in user space, but also in binaries running in kernel space. Of course, kernel exploitation is much more harder than normal binary exploitation because you cannot interact directly with the kernel. You are a user space program. You can only interact with the kernel indirectly through system calls. However, in kernel code, there still could be vulnerabilities. So by doing a lot of research, by doing a lot of study, like this kind of exploitation is extremely hard. I'm nowhere near to be an expert on this. But what I know is that with enough effort, sometimes certain vulnerabilities in kernel code can be exploited to obtain privilege escalation, to obtain execution as an administrator of the system. And this actually applies to both Windows and Linux. However, this is the Linux privilege escalation, so we'll stick with Linux. So this is it for this video. I hope it was fun, I hope it was enjoyable, I hope you learned something from this. If you did, please leave some feedback, leave some comments, tell me what you think of it, tell me what you want to see in the future, share this video with like-minded people, and see you to the next video.